Hello everyone. Following last video on abstract algebra, this video will continue on the content related to it. So I plan to introduce some tiny little stuff, and after that I will spend most of the time introducing an important concept called congruent classes. And that's it. Let's begin. So I would like to introduce a proposition first. This is related to last video on abstract algebra. What it says is, suppose that there is two numbers a and b. They belong to integers, and p is a prime number. If p divides a times b, then p divides a or p divides b. So here is a very straightforward proof. If p divides a, that's fine. So let's satisfy what we expected it is. What if p doesn't divide a? That means p and a are relatively prime. Since p is a prime and p cannot divide a, so that must have p and a are relatively prime. And from a theorem I have introduced last time, p divides a and b, and p does not divide a. That means p divides b. And that's a proof to this proposition. And now there is another tiny definition, and it's called binary operation. Basically, what it says is that if you take a and b belongs to a set, the same set, and there is a star represents any operation, arbitrary operation. When you conduct this operation, a star b, and you find out the outcome is still inside this set S, such kind of operation star is then called binary operation. Well, I guess this concept it's equivalent to say a set is closure. So you taken out two elements, and then after some kind of manipulation, and you find out the result is still within the set, and presumably I could say this set is closed. Okay, so then it comes to an important concept I would like to say more about in this video, and it's called congruent classes. The basic definition is this notion with one more horizontal line added to the equivalent sign. It's called congruent. A congruent to B more than. This is if and only if condition with A minus B is a multiple of N. This is a definition of congruent class. So there's a everyday example to illustrate this concept. When you look at a clock, in the morning there is 1 o'clock, and in the afternoon there is a 13 o'clock, and up to the name change, you know that it is literally the same thing. The longer hand and the short hand on the clock, the relative position of these two hands is exactly the same at least two time, 1 o'clock and 13 o'clock. That is because actually when these two numbers divided by 12, the remainder is the same. They both have 1 as a remainder. So, and then if you minus both sides of the expression, you will then find out this is where we get out definition from, the congruent class. And then we use such a notation, like square bracket, just to represent a group of numbers, a plus k times k times n, where k is arbitrary in integers. This is like basic concept, a definition regarding to congruent classes. And it follows with a theorism. If you have A congruent with B more than, then it's even and only if condition to say that congruent class A is more than is equal to congruent class B more than. And following, I'm trying to prove this theorism before we can then apply it into practical usages. So I will first prove the left to right, this side of the direction. We are given that A minus B is some multiple of n, say k2 times n. Then for a element belongs to congruent class A more than, and we can just expand out the expression, which is x minus A is equal to k times n, because we have such a kind of definition, and then we just rearrange it. And then this is what one side we are trying to prove, and adding up a new piece of information that A minus B is a multiple of n, and you just combine them together, and you find that x is equal to B plus n times some integer, and that is the definition for x to be an element in B congruent classes more than. And by the way, I would stress a little bit, how can we prove that these two sets are equal? You just take one element x inside one set, and then after some manipulation, you have proved that the same element belongs to another set. And since this element is arbitrary, we have no other external conditions regarding to this element, and then you just arbitrarily choose one element, and in the end you find that every element can be done in the same way, and then you will say that okay, these two sets are exactly equal sets, so you can done this kind of procedures. And this is the first direction, and the reverse direction may be even easy to follow. If you have two sets are equal, and that means A plus some multiple of n, say A plus k1 times n, and B plus k2 times n. These are both definitions for an element to lie within the set, and these two are equal. And then you just rearrange the expression. You will get exactly what we want in the reverse direction from right to left. A congruence with B more than. And we have then completed the proof. And that follows by another proposition, which is again a very used for propositions with regard to congruent classes. So suppose that a, b, c, d, and n are integers and n is greater than 0. If a congruent with b mod n and c congruent with d mod n, then we have these two properties hold. One is that a plus c, so you just add up these two expressions, these congruent expressions, and they still hold. A plus c is congruent with b plus d mod n, and a times c is congruent with b times d mod n. These two properties hold. And then again, this proof is quite straightforward. You just basically written out the expressions in full, and you can find out why. A congruent with B mod n, and then you change the expression into a normal equation. Oh no, the normal expressions we use. That is, A minus B is a multiple of n, and C minus D is another multiple of n. These K and K2 are distinct. They are not necessarily need to be the same. And then you just add up these two normal equations like the usual. And you can find out how this property is literally hold. And then if you times these two expressions together, you will find out these three terms are all multiples of n. That is n times a bracket something something something. And then we get the definition to prove property 2. And that ends the proof to this proposition. Purple colored proposition. And from this proposition, we are trying to define something new. So we define a binary operation, the addition and multiplication on Zn, such that we proceed the congruent classes as the normal, just as we plus two numbers, we multiple two numbers, and you can expect what the outcome is. And first thing is to check that it is well defined. Well, certainly this is closed because they are still the same a set of congruent classes. What they add and what they multiple. The result are always being a form of congruent classes. So it's certainly, undoubtedly closed. So we need to first check if it is well defined. That is, if we have two different congruent classes and we just add them up, if these two are equal, sorry for the previous if these two are equal, not distinct, if they are the same, the congruent classes are equal, well, the outcome of this addition and multiplication result in the same outcome of congruent classes. And apply with the purple colored proposition I have just mentioned above. You written out what it means to be congruent classes equal, and this also comes from a proposition, the first proposition actually. When I just now mentioned congruent classes, they are on the above sides. it's not quite clear. I will go back to that. So this series then tells us these two are equal. If we have two congruent classes, they are equal to each other. That means A is congruent to B more than. And that's why we can expand it out like that. And then we have another proposition. If we have two congruent classes like that, and we plus them together and times them multiply them together, and the congruent relationship still holds. That's that's the second proposition. And we have applied that to prove that this definition is indeed well defined. And according to the rules of division, that you can write A is equal to n times q plus r, where this r is a reminder and it is certainly less than n. And with our knowledge of being a congruent class, that's equivalent to say that A congruent with R more than, because A minus R is NQ, integer multiples of n. And then you know that, okay, congruent class A more than and congruent class R more than is the same. And since R can take values only ranging from 0 to m minus 1, so there are finitely many congruent classes modulo n from 0 to m minus 1 congruent classes more than. And they are all distinct. If not, let's say if not, there exist two congruent classes, they are equal to each other. And then you just written out the expression of the definition. And since R is within m0 to m minus 1, and so does S, and the largest possibility is m minus 1 itself minus 0, and the smallest possibility is you just reverse this expression to minus m minus 1. That's the smallest. And you want it to be divisible by n, and that's fairly impossible unless it is equal to 0, because others, they are all less than n. It cannot be n times some integers only when r minus s is equal to 0 and the condition is valid. But that means r is equal to s. So all these congruent classes, and there are n congruent classes, they are all distinct. And that leads to the final point in this video, that is to check if the multiplication and addition satisfy some properties. So in this case, is it commutative? Is it associative? And since the law, we have already defined it, and it can be manipulated in a very handy way. We can then check out it is indeed commutative and associative. And maybe in the next video, we will see that this is the basis for some elements to form a group. And they had to satisfy some specific properties. And that might be presented in the next video. And so, yeah, this is the all I would like to say in this video. and see you next time. Goodbye.